Hello and welcome back to the course on deep learning. In the previous tutorial, we found out what convolutional neural networks are all about, and today we're going to dive into step one, convolution. So, this is the convolution function. I know we try to stay away from mathematics and keep things intuitive, but I couldn't help but share this formula with you because it is so simple. A convolution is basically a combined integration of two functions, and it shows you how one function modifies the other or modifies the shape of the other. And if you've done any signal processing or electrical engineering or a profession where signal processing is required, you would have inevitably come across the convolution function. It is quite popular. Now, once again, we're going to keep the mathematics light or keep them separate. And if you'd like to get into the math behind the convolutional neural networks, a great additional read is Introduction to Convolutional Neural Networks by Jianxin Wu, who is a professor at the Nanjing University in China. This paper was published literally days ago, like 5 or 6 days ago, and it is oriented specifically at people who are starting out, at beginners who are getting to know convolutional neural networks. So the mathematics there should be accessible. I actually emailed Professor Xianxin Wu, and yeah, he said his whole goal is to make break the complex things down so that people who are new to this field can understand. And also he mentioned that he's got some materials available on his homepage. So if you, in the URL, if you just remove the last two parts and you just go to like /WJX to that part, that's his homepage, and you'll be able to find more additional tutorials and materials which haven't been published as papers, but he uses them in his tutorials. So you might find those useful. So browse around there if you'd like to get an introduction into the mathematics behind convolutional neural networks and kind of build a solid base around that area. But we're going to move on, and we're going to talk about the convolution. So what is a convolution in intuitive terms? Here on the left, we've got an input image, as we discussed. That's how we're going to look at images, just ones and zeros to simplify things. And you can see the smiley face there. Then we've got a feature detector. So a feature detector is a 3x3 matrix. Does it have to be 3x3? No, it doesn't. AlexNet, I think, uses 7x7. And then some other, one of those other famous ones uses like 5x5 feature detectors. They can be different, but usually you'll see that they are 3x3, and they are reasons to make them 3x3. So we're going to stick to the convention of having a 3x3 feature detector. Also, the feature detector is called, these are important terms because you might come across them. There are many different terms for the feature detector, but the most common ones are feature detector, or you might hear it being called kernel, or you might hear it being called filter. So in this course, we're going to be using either filter or feature detector interchangeably, but just bear in mind that it has those names. And a convolution operation is signified by an X in a circle, just as you saw on the formulas before. And here what happens is, on an intuitive level, or just to think of it in terms of what is actually happening in the background rather than the mathematics, well, you take this feature detector or filter and you put it on your image like you see on the left. So you cover the, for instance, in this case, the top left corner, the 9 pixels in the top left corner, and you basically multiply each value by each value, so respective values. So the top 0 by the top left value by the top left value, then basically position number 1 1 by a position number 1 1, position by a number, or 0 1 by 0 1, 0 2 by 0 2, and so on. So just it's element-wise multiplication of these matrices, and then you add up the results. So in this case, nothing matches up, so it's always either a 0 by 0 or 0 by a 1, so the result is 0. Here you can see that one of them matched up. The one on the left matched up, and therefore we got a 1. Here nothing matched up, nothing matched up, nothing matched up. Then we move on to the next row. So, and the step at which we're moving this whole filter is called the stride. So here we have a stride of 1 pixel. So here you can see again something matched up, the bottom right corner matched up. Again, stride, bottom one in the middle matched up. Here top right one matched up, then nothing matched up. The stride is 1. You can change the stride. You can make it 1, 2, you can make it 3, whatever you like. Conventionally, the one that works well is usually at 2, so that's what people stick to. And we'll talk about what the stride is towards the end of this tutorial. So here we've got we're matching up, so we just keep going. Oh, here you can see we've got a 2 because 2 of them matched up, and so on and so on and so on. There we go. There's another one that matched up. There we go, and there we're done. So what have we created, right? A couple of important things here. The image on the right is called a feature map. Also has several terms. It also can be called sometimes a convolved feature. So when you apply a convolution operator to something, it doesn't become convoluted, it becomes convolved. And yes, sometimes I think to myself in the wrong way, but it's the correct term is convolved. It's a convolved feature, or it can also be called the activation map, but we're going to be calling it a feature map in this course. So it can be called any one of those things. And what have we done here? Well, as you can see, we've reduced the size of the image. That's number one. And that's the important thing I wanted to mention about your input image and the feature detect and the stride, right? If you have a stride of 1, you can see the image reduced a bit. But if you have a stride of 2, the image is going to reduce more. So the feature map is going to be even smaller. And that's a very important function of the feature detector of this whole convolution step, is to make the image smaller because it'll be easier to process it, and it'll be just faster. It'll be just faster because imagine, like, here we've got a 7 by 7 image, but imagine if you have a proper photo, right? Or you have like a 256 by 256 pixel image. It's a huge number of pixels, right? 256 squared. Or like, let's say you have a 300 by 300 pixels. So we don't get confused with the RGB 256. Let's just say like we have a 300 by 300 image in terms of size in pixels. Then you have 300 squared number of pixels. That's a huge number. And therefore feature detectors will reduce the size of the image, and therefore stride of 2 is actually beneficial. But then the question is, do we lose information? Are we losing information when we're applying the feature detector? Well, some information we are losing, of course, because we have less values in our resulting matrix. But at the same time, the purpose of the feature detector is to detect certain features, certain parts of the image that are integral. And so, for instance, if you think about it this way, like the feature detector has a certain pattern on it. The highest number in your feature map is when that pattern matches up. In fact, the highest number you can get is, in a now simplified example, is when the feature matches exactly. And you can see with that number 4 we have in our feature map, that's exactly, so if you look over here, that's exactly where this feature detector, because there's only 4 ones in it, matched perfectly. So you can see this part over here. So the feature was detected here. And as we discussed at the very start of this section, that is, features is how we see things, is how we recognize things. We don't look at every single pixel, so to speak, in what we see on an image or in real life. We don't look at every single pixel. We look at features. We look at the nose, the hat, the feather, the the eyes under, or the little black marks under the cheetah's eyes to distinguish it between a cheetah and a leopard, or the shape of the train. We don't to distinguish it between a bullet train and a normal train, and so on. So we don't look at everything, we look at features, and that's what we're preserving. And that's what the feature map helps us preserve, actually. That's what it allows us to bring forward and get rid of all of the unnecessary things that even as humans we don't process. There's so much information going into your eyes at any given time, like gigabytes of information. If you look at every single dot, if not terabytes of information going into your eyes per second, and still we're able to process that because we get rid of what is unnecessary. We only focus on the important features that are important to us. And that is exactly what the feature map does. So now moving on, this is our input image, and we create a feature map. So the front one, let's say the front one is the one we just created. But then how come there's many of them? But we create multiple feature maps because we use different filters, right? And that's another way that we preserve lots of the information. So we don't just have one feature map. We look for certain features, and then or basically the network decides through its training, and this is something we'll discuss towards the end of this section, through its training, it decides which features are important for certain types or certain categories, and it looks for them, and therefore it'll have different filters, and we'll talk about filters just now. But basically it'll apply these filters. So to get this feature map, it applied a filter like the one we saw. But then to get this feature map, it applied a different filter. To get this feature map, it applied a different filter, and so on. And so basically it just creates these feature maps. And actually that's why personally I think the term feature detector is better than filter. So remember over here we have this filter, which we also can call a feature detector. Well, actually the word feature detector I think is better suited. And the reason for that is that's what the purpose is, right? We don't want to just filter out our image, but even though that's the same, just we're a question of terminology. But basically we want to detect features. All right, in this layer, we're going to, or in this feature map, we've detected where certain features are in the image. In this feature map, we've detected where certain other features are, where a certain specific feature is located. In this feature map, we've detected where a certain other feature is located on the image. So that's what we're doing, and let's have a look at a couple of examples. So here we're using, and this is from gimp.org, their documentation. It's a free like a kind of tool like Paint, and you can use it to adjust your images or work with your images. But basically they have some valuable examples in their documentation, and here they have a picture of the Taj Mahal, and you can choose which filter you want to apply. So if you download this program and you upload a photo into it, and then you can actually start a convolution matrix and apply filters, and you will see that these convolution matrices are actually applied in image processing and design and so on. So let's have a look at what we get. So if we apply this filter, 5 in the middle, -1, -1, -1, -1, you can see that it sharpens the image. And yeah, so it's quite intuitive if you think of it. So 5 is the pixel, the main pixel, like in the middle of the filter or the feature detector. And then -1, -1, -1 just kind of like reduces the pixels around it in an intuitive sense. Then blur. So basically it takes gives equal significance to all of the pixels around the one in the center, and therefore it combines them together and you get a blur. Edge enhance. So here you can see that -1 and 1, and then you get zeros, right? So you remove the pixels around the main one in the middle, and you only keep this one at a -1. and it gives you an edge. And this one's a bit harder to understand how it works. Like probably harder just to think of it intuitively. Edge detect, right? So this one probably makes more sense, right? You take the middle one, you reduce the middle one, probably like the strength of the middle pixel, and then you look for the ones, you look for these ones, you increase the strength of the ones around them, so you have the ones there. Yeah, so that gives you like an edge detection, and you can see what you get there. Emboss, another one. So the key here is that it's asymmetrical, and you can see the image becomes asymmetrical as well. So you got like that kind of feeling that it's standing out towards you, and that's what you get when you have like minuses here and pluses here. Again, this is getting a bit technical now, but at least we can get some kind of intuitive understanding. Let's just go quickly through them again. So there's sharpen, there's blur, there's edge enhance, there's edge detect, there's emboss. And so as you can see, these are great examples of the same image, but we're getting feature maps. So we use different feature detectors to get different feature maps of the same image. And therefore now we have lots of this versions of this image, where in each one we've tried to detect certain things. These terms, they're not applicable to us. They're, except like emboss is probably not applicable to us in terms of convolutional neural networks, but edge detect, that's important. We want to detect the edges. Edge enhance, probably not. Blur, sharpen. So certain things like edge detect is probably the most important one for our type of work. And in terms of understanding, like computers, they will decide for themselves. Their neural network will decide for itself what's important, what's not, and it probably won't be even recognizable to the human eye. You won't be able to understand what those features mean, but the computer will decide, and that's the beauty that of neural networks, that they can process so many different things and understand without even having that intuition, without having that explanation why. They will understand which features are important to them, whether we have a name for them or not. That's an irrelevant question for the artificial neural network. And my favorite one, here's a image of Geoffrey Hinton, a photo of Geoffrey Hinton passed through one of these filters. All right, so that brings us to the end of today's tutorial. I hope you enjoyed learning about convolution. The key takeaway is that convolution, the primary purpose of a convolution is to find features in your image using the feature detector, put them into a feature map, and by having them in a feature map, it still preserves the spatial relationships between pixels, which is very important for us to because if they're completely jumbled up, then we've lost the pattern. And at the same time, it's important to understand that most of the time, the features a neural network will detect and use to recognize certain images and classes will mean nothing to humans, but nevertheless, they work. And that's what convolution is, and I look forward to seeing you on the next tutorial.